Hello, we are Group 1 Biological Remediation Methods. Bioremediation is the use of either naturally occurring or deliberately introduced microorganisms or other forms of life to consume and break down environmental pollutants in order to clean up a polluted site. It can be used to treat contaminated media, which includes water, soil, and subsurface material. Bioremediation is supposed to be a relatively low cost and simple method, so it is looked at quite frequently as a cleanup option. As you can see in the figure, bioremediation is broken down into two main ways, ex situ and in situ. Ex situ means that contaminated material is removed from the site and remediated elsewhere. In situ remediation is when a method is introduced to the environment where the contamination is. The ex situ methods pictured here are biopiles, windrows, bioreactors, and land farming. The in situ methods pictured above are natural attenuation, bioslurping, bioventing, biosparging, phytoremediation, and permeable reactive barriers. The enhanced branch means that it is enhanced from the natural processes through some way, which is where they get the fancy names. We'll start with the ex situ methods. Biopiles involve piling mounds of excavated, polluted soil, introduction of nutrients, and sometimes the introduction of an aeration system to enhance the microbial activity. The basic components are aeration, irrigation, nutrients, leachate collection, and a base treatment bed. Basically, the irrigating nutrients and aeration are to increase the rate of degradation that occurs via the microorganisms. This method can also be temperature controlled to be at the microbe's prime activity temperature while possibly offsetting cold temperatures at the remediation site. The picture here shows all the typical aspects of a biopile system. You can see that it is a mound of contaminated soil covered by a liner with inputs of air, water, and nutrients. You can also see the leachate collection system underneath the treatment bed. There is no temperature control here because sometimes that system can dry out the bed itself and lead to volatilization, which is not what you want. Windrows rely on periodically turning piles of polluted soil to increase bacterial and microbial activity in the degradation process. The increased activity is due to an increase in aeration from the turning, adding water if necessary, and uniformly distributing the pollutant and nutrients. It can sometimes lead to buckets of anaerobic zones which lead to the production of methane, the greenhouse gas. It is not as controlled as biopiles. Here you can see how one row in the system would look. You can see the piece of equipment that is used to turn these over. There are no covers or pumps like in a biopile system, so there is more of an enhancement on natural attenuation, just at a site separate from the contamination source. Bioreactors are systems in which raw materials are converted to products via biological reactions. They can be operated in modes such as batch, fed batch, sequencing batch, continuous, and multi-stage. Polluted samples can be fed into the systems either dry or slurry based. Microbial activity then breaks down the pollutants into products. Bioreactors try to control the variables temperature, pH, agitation, aeration, substrates, and microbe concentration to have the system running optimally. It requires a lot of experimentation to get the ratio of everything just right, plus it can only handle a limited input flow rate. In this diagram you can see all of the variables that can be controlled in a bioreactor. There are sensors to monitor pH and contaminant levels, and there is a thermal jacket to regulate temperature. There is also an aeration system. Land farming is when polluted soils are excavated and or tilled. The contaminated soil is laid out on top of the ground where it is irrigated and naturally aerated to promote microorganism activity. This type of bioremediation can be considered in situ or ex situ depending on the depth of the soil that it is excavated and tilled. If it is less than 1 meter, it is treated as in situ, but if it needs to be excavated, it is considered ex situ. As you can see from the image, this type is close to windrow, except the material is not being made into long mounds, It kind of looks like a very confined crop farm, but in this case we are growing microbes instead of crops to degrade the contaminant. Now we switch to the in situ methods. Natural attenuation is a passive remediation of polluted sites. There are no external human interactions to increase microbial activity. It relies solely on aerobic and anaerobic microbial activity to achieve the targeted concentration. This method involves careful monitoring and experimentation to establish the microbes that can degrade the pollutant in the first place, and that it is actually degrading the concentration over time. It may take a while to reach the target concentration because it is not being expedited by human interactions. Here is a basic example of natural attenuation. They are letting the microbes in the soil and water take care of the degradation while monitoring the concentration of the mobile plume via the monitoring well. Bioventing is the controlled stimulation of airflow by delivering air to the unsaturated vadose zone so as to increase the degradation by microbes already in place. In some cases, nutrients in water are also added to stimulate the microorganisms. The air injection rate is one of the main parameters/variables to consider because depending on the contaminant, a low or high injection rate is best. Here you can see a very basic setup of air being injected into the vadose zone. There are no monitoring wells pictured here, but that is a big thing that is missing. Bioslurping is a combination of vacuum-enhanced pumping, soil vapor extraction, and bioventing to get remediation increases by providing aeration and water. It's mainly used for L Naples so it can remediate capillary, unsaturated, and saturated zones. The system itself uses a vacuum like a straw to slurp up liquids containing free product and soil gas. The L Napple becomes separated from air and water, making it a bioventing process after the L Napple has been mainly removed. Here is a setup for a typical L Napple contaminant, hydrocarbons. You can see that that slurp goes down and takes up material and is separated into water and gas treatment sections. You can also see the aerobic biodegradation taking place outside of the slurp. Biosparging is very similar to bioventing in that air is injected into the soil to increase microbial activity. The difference is that it's injected into the saturated zone to promote the upward movement of VOCs to the unsaturated zone to be degraded. Its effectiveness depends on soil permeability, which determines pollutant availability to microbes. In the figure, you can see that air is injected into the saturated zone, and it promotes movement upward to where it is degraded in the vadose zone. Then the vapors can be treated on the surface by a soil vapor extraction system. Phytoremediation relies on plant interactions with pollutants to degrade or reduce the harmful concentrations. Elemental pollutants like heavy metals and radionuclides are removed by extraction, transformation, and sequestration by the plants. Organic pollutants like hydrocarbons and chlorinated compounds are removed through degradation, rhizofiltration, stabilization, and volatilization. You need to know what type of plant can deal with what type of pollutant. You also need to know if your plants have fibrous roots or a taproot. They can be used hydroponically in large aquaponic systems or in simulated wetlands. Here you can see how the plant can interact with the polluting substance. The volatilization could be an issue because you do not want harmful gases being released into the atmosphere. Permeable reactive barriers are a permanent or semi-permanent reactive barrier made up mostly of zero-valent iron, which are submerged. If water flows through the barrier and under its own gradient, pollutants are trapped and undergo reactions that result in clean water flowing out the other side. You can see the permeable reactive barrier at work in the figure. The contaminated water flows in one side and undergoes natural chemical reactions where the pollutant is eliminated and clean effluent comes out the other side.
In this section, we'll talk about the influencing factors. The processes associated with bioremediation that are applied to remove, degrade, or detoxify pollutants within the environment. 4 processes that act on the contaminants are the removal, which is the physical elimination of pollutants from the environment without the need of separation from the host; separation, which removes the contaminant from the environment; destruction or degradation, which chemically or biologically destroys or neutralizes the contaminant to less toxic compounds; and containment or immobilization, which impedes the surface and subsurface migration of contaminants. There are two different techniques that you can use within bioremediation of ex situ and in situ, which will be discussed later in the slides. Determining which one depends on several factors, such as cost, site characteristics, and type of concentration of pollutants. The two main groups of factors that influence bioremediation efficiency are contaminant properties and environmental conditions. Of the two contaminant properties, there are toxicity and concentration. Toxicity prevents or slows metabolic reaction and can often prevent the growth of new biomasses needed to stimulate rapid containment removal. The pollution of heavy metals, nuclear waste, pesticides, greenhouse gases, and hydrocarbons are of the greatest threats to living organisms in an ecosystem. Metal toxicity is a great environmental concern due to the bioaccumulation and non-biodegradability in nature. Inorganic metals such as magnesium, nickel, chromium, copper, calcium, manganese, sodium, and zinc are vital elements used in small quantities from metabolic and redox functions. Heavy metals such as aluminum, lead, cadmium, gold, mercury, and silver don't play any biological role and are considered to be toxic to living organisms. Concentration. At low concentrations, contaminants may remain undegraded or be biodegraded extremely slowly. It's usually caused from unavailability in which the contaminant is sequestered from microorganisms. At high concentrations, some chemicals are too toxic to microbes. An additional thing that can happen with concentration is intermediate buildups. Dead end products, which can be created, are formed during co-metabolism that bacterial enzymes cannot transform or break down any further. Another example of intermediate buildup is when a compound can fully be degraded, but it still forms the buildup. Toxicity and high concentration levels could pose a threat to microbial species acting in the system if one or more of their essential steps in the myriad physiological process is blocked. Environmental conditions consist of temperature, moisture content, pH levels, nutrients, and the addition of biosurfactants. Enzymatic reactions rate increases proportionally with temperature, so it is ideal to have relatively warmer conditions. However, most enzymes reach an upper limit of production at temperatures above 40 degrees Celsius. Depending on the types of microorganisms being used, different moisture levels within the surface or other contaminated matter are required for the microorganisms to be most effective within the bioremediation process. Another thing to consider is sequestration, which occurs when the contaminant is dissolved in a non-aqueous phase liquid or liquid that doesn't readily mix with water and thus travels through the ground separately from the groundwater. It can also occur if the contaminant is strongly absorbed into the soil surfaces or is trapped in pores that are too small for circulating groundwater. The pH is to be taken into consideration because most microbial species can only survive within certain pH ranges. It also has an effect on the availability of nutrients. The ideal pH range is usually a neutral one, which is from 6 to 8. The addition of nutrients such as vitamins, substrates, and oxygen can help stimulate microorganism activity and degrade contaminants faster. Combinations of inorganic nutrients such as phosphorus and nitrogen are often more effective than single nutrients in accelerating biodegradation. Finally, with the addition of biosurfactants, they can provide an additional means of improving treatment by increasing the surface area of hydrophobic hydrocarbon compounds and more exposure to microorganisms. Certain removal processes exploit the ability of biomimetic adsorbents from removing trace amounts of organic contaminants that originated from aquatic animals. Biomimetic materials are developed using inspiration from nature. They pose some advantages, such as they have excellent sorption capacities due to their porous and lipoptic natures. They can be considered as environmentally friendly products because they are biodegradable and innocuous, and the waste they produce can be reused. The use of biomimetic adsorbents is based on the capacity of materials used as biological lipids to immobilize trace pollutants which can exhibit low water solubility.
For field implementation, there were 6 different methods that were discussed. The first one is bioreactors. A bioreactor is a device that supports a biologically active environment in which a chemical process is carried out. This involves organisms and biochemically active substances. These substances can either be aerobic, which is the need for oxygen to survive, or anaerobic, which is the need for no oxygen or oxygen phobic. Bioreactors can be as crude as a trench in the ground, which submerged liquid is infiltrated into the ground and it can immobilize or suspend contaminated solids and other particles, or it can be as established as an enclosed metal reactor that can create anaerobic conditions and has control over multiple factors in the experiment. This establishes the different conditions for the waste biotreatments, which can include harmful gases that are produced, such as carbon monoxide and high volumes of carbon dioxide, high amounts of heat, and the need for constant monitoring. There are 3 different kinds of bioreactors. The first is a continuously stirred tank reactor model, or a CSTR, a plug flow, or a batch. The choosing of the 3 different kinds depends on the environment that um, you are looking at, then contamination, the duration of the process that needs to take place, the volume of the contamination, and other surrounding factors such as the environment or whether or not it needs to be continuously monitored. The second method that was considered was biopiles. Biopiles are piles of contaminated soil used to degrade the contaminated microbes within the soil using runoff and aeration techniques. These are used to treat aerobically degradable organic compounds, which are broken into 2 different groups: volatile organic compounds, or VOC, and semi-volatile organic compounds, or SVOCs. VOCs are indoor and outdoor pollutants and are defined as any compound of carbon that may occur, excluding carbon monoxide, which participates in atmospheric photochemical reactions. This reaction will create an aroma, which allows us to distinguish if these VOCs are being produced. Vice versa is VOCs, which are considered part of VOCs but have a higher boiling point, and thus they are not as noticeable because they create no aroma, which makes them more dangerous. Biopiles have many limitations that come with the method to be used, such as constant temperatures, change in temperatures, the volume of high bulking material that is needed, air pollution that can arise from these, and heavy metals that are not treated that can be toxic to the environment when reintroduced. Because of this, these implementations are generally considered to be short-term technologies to remove intermediate chemicals and are not the best method to be used. A third method that is chosen is phytoremediation. Phytoremediation is defined as a group of technology that uses plants for remediation of soils, sludges, sediments, and contaminated water with organic and inorganic contaminants involved in them. In other words, the use of plants to remove, detoxify, and immobilize environmental contaminants within a specific matrix of either air, water, or soil. Phytoremediation can be used for the removal of metals, pesticides, solvents, explosives, crude oils, specific hydrocarbons, and landfill ligates. Phytoremediation is when plants are able to evolve to absorb the contamination and are able to metabolize it in their cells. From there, these plants will be harvested, processed, and if need be, they will be disposed of, which can allow the environment to return to its natural state when it does come in contact with contaminants.
Another way to apply biostimulants or bacterial cultures are the biobarriers, which minimize the movement of contaminants. These are installed by digging a large trench. They are usually no more than 50 feet and 20 to 50 feet deep. Heavy machinery is required for the digging, like an excavator or a bulldozer. Once installed, these require minimal maintenance. Bacteria are often used outcompeted on endogenous cultures. Another method is biostimulations, which, uh, which uses bioventing that blows oxygen and other compounds with a blower to stimulate biodegradation of organic compounds. Bioventing uses low airflow rates to provide only enough oxygen to sustain microbial activity in the vital zones. Requires monitoring well for movement of contaminants and employs an injection system which apply the additives to the subsurface. Require multiple equipment like compressors and ventilators. Finally, another method used is bioaugmentation, which introduces bacteria with activated sludge to the environment to activate biodegradation into contaminated soils. It is commonly used in municipal wastewater treatment to restore activated sludge bioreactors and employs an injection system as well for oxygen and bacteria culture injection.
A remediation company in Arizona was selected to complete a remedial action plan for soil contaminated with crude oil located in an oil production field in Texas. The crude oil contaminated soil was generated from storage tank bottom material, which had been removed from several oil recovery storage tank batteries located within the oil field storage facility. The soil was stored on site for approximately 5 years, with periodic addition of material to the storage pile. Bioremediation probiotic technology was chosen using probiotic solutions products for the pilot study cleanup and mitigation of the petroleum contaminated soil materials. Treatment of the soil began on July 27th. The soil pile was spread out over an area approximately 200 feet in length and 30 to 75 feet in width. The depth of the soil was approximately 12 to 18 inches. All areas surrounding the pile were protected by an earthen berm. A large bulldozer was utilized to spread the materials over the land treatment unit area. The soil being spread was highly saturated with oil materials as described above. The tank bottom materials were not easily spread because of the liquefied stage they were in. The material exhibit the characteristic of wet cement when being spread. The contaminated material was inoculated only twice during a month period. The soil was inoculated by surface application to guarantee that the probiotic products and water were applied efficiently to the soil materials. The nutrients and other probiotic complexes were pre-mixed in a 500-gallon tank and were then applied under high pressure into and onto the soil. The indigenous organisms were utilized because of the established microbial populations that had developed over the 5-year period of time that the tank bottom material had been stored on site. The soil contained in the LTU received approximately 3,000 gallons of water per inoculation. The water was utilized as a carrier for probiotic solution products. The soil was mixed and surface irrigated periodically to ensure proper soil moisture availability, approximately 30% moisture content. The soil pile was aerated mechanically with a tractor and mechanical mixing device. The aeration process coupled with probiotic solutions products provided sufficient oxygen and necessary nutrients for the microbiological ecosystem in the soil to effectively reduce the TPH concentrations. For the case study 2, soils treated in this case was excavated during the remediation program conducted as part of decommissioning a well site in 1999. Preliminary remediation work was completed between December 1999 and May 2000. Soils impacted by salts and metals were excavated and hauled to a secure landfill. Laboratory results indicated that approximately 4,000 cubic meters of soil were impacted with hydrocarbon-based compounds only. Soil samples were collected from the treated area to confirm the success of the remediation program. Soils were mixed with a track hole equipped with a mixing unit. At the time of mixing, amendments were added to ensure adequate nutrients level in the soils. Once soils were mixed, the material was placed in biopiles that range from 0.75 meter to a maximum 1.5 meter height. This ensures that the diffusion was able to supply oxygen to the core of the biopile. No further aeration activities were conducted at this site. Remediation with the mixing head appears to have reduced the level of contaminants to less than lab detection limits for BTEX and below criteria in the cases of PHC fractions F1 to F4. Although the pathway of contaminant reduction occurred was not evaluated, it is possible that volatilization may have played a role in this case. Addition of nutrients may have enhanced the biodegradation process as well. Table 2 summarizes the analyzed parameters of concern for the impacted soil. All analyzed parameters, except for the electrical conductivity, were below criteria. This factor may be related to the high solubility of nitrogen fertilizer that were added at the time of remediation program. EC levels were about 2.9 ds per minute in the confirmatory samples. Although it is above criteria, transformation of nitrogen ion to organic matter and leaching due to rain events may reduce EC levels.
A bioreactor consists of an engineered vessel that creates an environment that promotes biological growth, allowing the reproduction of microorganisms in hopes of taking advantage of a chemical process that will take place as a result of these organisms feeding. This remediation method is considered to be both aerobic and anaerobic, meaning that it can be applied to several different substances requiring a large range of chemical processes in order to degrade the contaminant. One of the most common applications of this remediation method is sewage treatment. The main goal of this process is to take wastewater and convert it back into an effluent where it can then be returned into the environment without any hazardous effects. The bioreactors create an environment where microorganisms can thrive, and their presence will speed up the decomposition of organic wastes through their normal cellular processes. Once these wastes are broken down, it is much easier for someone to dispose of these hazardous materials, and the wastewater is one step closer to being returned to the water cycle. Although this process is oftentimes considered a secondary treatment, it is very effective in assisting the removal of organic waste and is a rather economical method as it does not require many expensive chemicals or machines. One major limitation of this biological remediation method is that it is considered to be an ex situ remediation method. The reason this is a limitation is because this limits the scope and the rate of remediation that is possible. Ex situ remediation means that you must remove the contaminated wastewater and transfer it into the bioreactor tanks in order to create proper conditions for the most effective decomposition of waste. This means that the amount of water that you can effectively remediate and the rate at which you can do this is limited, because of the limited volume of the tanks and resources of the organizations funding this remediation. A biopile is a remediation method which consists of a large mass of excavated soil which is then mixed with soil amendments, which are substances that will help to improve the overall quality of the soil. The soil is then aerated and the VOCs are removed. The most common application of this remediation method is to attempt to decontaminate large sections of soil of non-chlorinated VOCs and fuel-contaminated soil. One of the major limitations of this method is again that it is an ex situ process, meaning that the soil must be excavated and then transported to the biopile apparatus. This process will mean more costs, and the ex situ method limits the amount of soil you can treat and the rate at which you can do so. Another limitation of this method is that it is difficult to remove more than 95% of the VOCs from the soil with this process. This means that it is unlikely that you will completely rid the soil of the VOC, and this limits your ability to completely remediate. This process is also limited by the type of VOCs it can treat, as its effectiveness varies by the type of contaminant. For example, the effectiveness of removing chlorinated VOCs from soil is not reliable and may not work to the full extent. Phytoremediation is the in situ process of using living plants and trees in order to assist in the breaking down of contaminants in soil and groundwater. This process has been used throughout the world in order to remove metals, pesticides, solvents, explosives, and cruel oil from soil and groundwater. This process, although low cost and environmentally friendly, does have several downsides that may deter people from using it. One of the main limitations of this process is that it requires a large commitment of time, as the process of growing plants is not done quickly. Another limitation of this process is that you can only reach contaminants that are within the range of the roots of the specific plant. This makes it not possible to remove contaminants that are located at a depth below the roots. A final limitation of this process is that since you are trying to remove contaminants with living plants, means that the environment that you are growing the plants in will contain contaminants that may be toxic to the plants, making it more difficult to grow the plants and keep them alive. A permeable reactive barrier is a type of in situ remediation which consists of a membrane being inserted into the water table and removing contaminants from the water that flows through it, with the help of chemicals that are inserted into the membrane. The applications of the permeable reactive barrier are mostly targeting VOCs, metals, and various radioactive materials. This membrane is used to filter these harmful substances out of the groundwater. One of the limitations of the permeable reactive barrier is that it is difficult to remove the entire plume of contaminant, meaning some will stay in the groundwater. Another limitation of this method is that it is very hard to install the barrier, as you usually have to dig around 80 feet to get to the water table. This means a large deal of resources will be required for installation. One final limitation would be that the chemicals included in the barrier that are meant to react with the contaminant could possibly leach into the water and become a contaminant themselves.
In cost and availability, I will talk about 4 different cases and estimate the cost of them in the units of dollar per mass or volume. First, what's included in a basic wastewater treatment system? An oil-water separator, a series of reactors and chemical additions, filtration, pipelines and control panel. A wastewater treatment plant can cost about $500,000 to $1.5 million. Such a system can work at the rate of 150,000 GPD, cost about $2 per 1,000 gallon. A biological wastewater treatment plant in flow rate of 1,200 cubic meter per day and biogas production of 4,800 cubic meter per day costs about $1 per cubic meter. Active sludge wastewater treatment plants with flow rate 50 million gallon per day can cost about $5 per million gallons. A leachate system has an average cost of $0.03 to $0.12 per liter. And the last case, bioreactor. The non-hazardized solid waste of bioreactor costs $35 per ton. Hazardous solid waste costs $145 per ton. The liquid waste costs $0.5 per cubic meter.
Here is an example of a simple phytoremediation system.
The poplar tree. It's a fast-growing and versatile plant ideally suited for producing renewable fuels and other products that are usually derived from petroleum. It's also widely grown to produce wood and paper products. But even more, it's a particularly effective resource for recycling treated wastewater from our cities and cleaning contaminated soil on industrial sites while reducing carbon in the atmosphere. In the Pacific Northwest, poplar trees are grown by many municipalities to recycle treated wastewater, improve water quality, and reduce waste. At the same time, the trees produce woody biomass that has additional economic value. As wastewater is collected, it's transferred to a wastewater facility for treatment. This typically involves removing organic solids, which can be made into a soil amendment and used to fertilize poplar growth instead of going to a landfill. The remaining clarified water is further treated through microbial processes and disinfection. The water can then be recycled for returning the treated water to streams and rivers or for irrigating poplars, which can further purify the water by taking up additional nitrogen and phosphorus. Poplar trees are an excellent crop for recycling water and nutrients, while also sequestering carbon and contributing to other community sustainability goals. Another exciting application of poplar trees is for phytoremediation and cleanup of industrial sites. Phytoremediation is the practice of using plants to stabilize or reduce contamination in soils, sediments, surface water, and groundwater. Poplars remediate by absorbing and concentrating nutrients, including nitrogen, phosphorus, and ammonia, at their roots, enhancing soil microbial activity, and breaking down contaminants within the plant tissue. In addition to absorbing nutrients and contaminants, poplars can also prevent topsoil erosion, help restore riverbanks, provide carbon sequestration, enhance habitat for wildlife, create beautiful landscapes, and provide effective riparian buffers. Advanced Hardwood Biofuels Northwest supports municipalities growing poplar for recycling wastewater and industrial facilities growing poplar for phytoremediation. These trees may also be used in the future to provide renewable fuels and bioproducts.